All right. So thanks everyone for coming. Our presentation is going to be on computer vision-based anchoring in multiplayer augmented reality systems. A little bit of a mouthful. Let's dive into what some of these words mean. Start off the team. I'm Krishna.
I'm Akshat. I'm Jacob.
I'm Amit.
And Devesh.
And our team was advised by Professor C.J. Taylor. So what is augmented reality? So augmented reality is the placement or projection of computer-generated assets onto the real world via a camera, a lens, or some form of screen. We've seen this become really popular in the last year with games such as Pokemon Go, but many, many other applications. As you can see, now there are 600 million AR-enabled devices. What does this mean? This means your Android device, your iPhone device can now have access to augmented reality games. In addition, the biggest use case so far is mobile gaming, $45 billion industry that's growing super rapidly. But there's so many more applications to augmented reality than just gaming. Just think about the healthcare space. If you are a professor and you're trying to teach your students about how the human body works, but you don't have access to such things, augmented reality could place a cadaver inside your classroom and have everybody around you look at it and interact with it. Current applications of multiplayer or of augmented reality are generally single player. What this means is that I can see something in my screen. If I put my phone out, I can see an asset, but the people around me aren't able to see that. And that's a very tough challenge, as we're going to go into in a little bit. And so our goal for this project was to create a framework that would allow developers of augmented reality applications the ability to create their own multiplayer experiences. I'm going to pass it off to Amit to talk about how this works.
Thanks, Krishna. So first, basically, I want to give us what is the lay of the land as far as multiplayer augmented reality experiences right now. So as Krishna mentioned, the two chief software packages basically released by Apple and Google are ARKit and ARCore for Android and iOS. And so what do they provide us as far as tooling and facilities for making multiplayer possible? There's kind of three distinct areas. So the first one being synchronization between two clients. So once two clients know where everything is, how do we all make sure that everything stays in the same place and all of the updates and movements are transmitted to all the clients? So this is a largely solved problem. It works with many other games as well. The idea of keeping track of assets across many clients. Next, there's tracking. So once we've placed an object in the world, when a person moves, obviously it should look like you're moving relative to whatever asset you've placed for augmented reality to be convincing and intriguing. So this is taken care of through a combination of computer vision techniques and use of the phone's gyroscopic sensors. And then finally we come to localization, which is the chief challenge that multiplayer faces and what we as a team worked on the most to tackle. And localization basically means getting that initial lock on the world, getting some anchoring such that two people or more can actually agree on where an object is and what orientations they are relative to that. So that has two pieces. So one being, for example, the actual translational. So for example, if Jacob and I were trying to share an object in the middle of the stage here, we would have to know how far the object is from Jacob and how far it is to me to properly render its size. And the other being rotational. So for example, if the object we were rendering was a large Rubik's Cube, Jacob should be able to see one side of it, whereas I should be able to see the other two sides of it from here. And so basically, we had to tackle both of those in order to make multiplayer possible. So what do current games look like? How do they solve this key challenge? They pretty much solve it by asking the user to manually resolve all of that for them. So basically, for example, in this game, the machines, basically, you'll basically place a mat that will literally tell your phone where everything is exactly. And from there, once the initial lock has been made, the synchronization and tracking are done by ARKit or ARCore. Next, I'll pass it off to Akshat.
Cool. So there's a couple of problems with this approach that Amit just described, right? Number one, it takes an incredibly long time to set up and calibrate. As you can see, that GIF is almost 20 seconds long. And even during that time, the person is not done setting up the app yet. So the user can't actually play the game. Two, the results are pretty unreliable, right? You're relying on two people to position some virtual object in their environment the exact same way on two different screens. So inherently, there's going to be some level of inaccuracy here. And three is that this whole screen that you see, the whole development process, the whole process to position this table has to be customized for every single application. So that's a huge challenge for developers, especially smaller developers who don't necessarily know this pipeline. So these are the three issues that we kind of set out to solve with our solution. And we set out to build a pluggable framework that would automatically and efficiently select anchors using computer vision. Now, what that means is that a developer could quickly take our software package, right? One-click deploy a server, drag a couple of our scripts into their development environment, and suddenly be all set up to start sharing different assets across their two clients in augmented reality. So how did we go about actually building this product? So we identified three highly parallelizable workflows from the very start. One is the client side, which Devesh and I worked on. Two is the server side, which Jacob and Amit worked on. And three is the developer side considerations, which Krishna worked on. We also adopted a multi-tiered approach to solving this problem, which meant that at the end of each milestone, we wanted to have a testable working product. So for milestone one, we actually didn't set out to do computer vision off the bat. We decided to build out a manual solution, like the one we just saw in the GIF, because that would allow us to test out the rest of our networking and synchronization pipeline, and it would allow us to ensure that the product was actually easy for developers to use, which was a day one consideration. Once we had all the infrastructure laid out and working and tested, then we actually went in milestone two and added in the computer vision element. This allowed us to zoom in on the problem, the hard part of the problem, and tackle that individually instead of along with all the other baggage that came along with the app. Finally, once the basic app was working, we optimized for performance across the entire application, from the client side to the server side. We also had time at the end to build a small UI demo, which you'll see later. So I'm happy to report that with this approach, we were able to accomplish all three milestones. And Jacob will go into how that kind of performed later on in the presentation. So how do we know that what we've built at the end actually solves the problem? So at the very beginning, we went out and set out a bunch of criteria that we wanted to compare ourselves against when we were done. So first, that first problem I mentioned, setup time and calibration. So we wanted to reduce the amount of time it takes to actually set up the app, right? Both in seconds, and we also wanted to make sure that the server returned our anchor in an efficient manner. Finally, we wanted to ensure that the quality of the anchors generated were actually good, and this is something that we'd have to manually inspect. The application latency, we wanted to aim for it to be as low as possible across, so from me moving an object, from that updating locally, going to the server, going to the other client's phone, and updating on their side. And finally, the developer overhead. We wanted this to be as easy as possible for developers. So the number of lines of code it took to actually spin up our server and to actually integrate our framework into the application should be minimized. Now Devesh is going to talk to you about how exactly the computer vision aspect of this works.
Awesome. So I'm super excited to talk about this. This has been what we've been working on for like a year right now, and this is super exciting. So if you look at what the problem is, we have two phones that are looking at a common real-world object, and in this example, that's just a desk or a desk drawer. What we're looking at is each phone. A phone has a camera, and that camera has a view frustum, and that's sort of modeled out for this phone, and similarly for another phone. The core problem is that we have two phones looking at the same world object, but through different perspectives and rotations. What we want to solve is say, find that common desk drawer handle and say, this is the same object in both phones' perspectives. And it's a really hard problem. So if you look at what's happening for each phone locally, they individually have some sort of idea of how far away the desk is from the phone itself, different common feature points that it can recognize as having some sort of real-world coordinate system relative to the phone's position. And this is all information that's local to each phone. So each phone sort of knows that I'm looking at the desk drawer from this perspective, and another phone knows that I can see another desk drawer, but they have no idea it's the same one. So what we wanted to do is join these two images together. So taking the images from each phone, we send them across to our server, and when we split them across, we now have, on the server, these two different features. Our overall goal is to sort of say we have points in the first image and points in the second image that correspond to each other. So what we initially thought would solve this problem for us immediately was an algorithm called SIFT. SIFT is an image recognition algorithm that takes 2 images, 2D images, regular images like you could take from your phone right now, and says we can generate key points in image 1 that correspond to key points in image 2 and give you back a set of matches. And they give you back a lot of matches, about almost hundreds of matches. And these are key points that are generated purely based on the image itself. So we thought this would be a good solution. We thought we could use these matches and figure out what it is would correspond to each phone. But we realized really quickly that these weren't the best matches. In fact, you can tell quite quickly that the points generated by SIFT are edge boundaries, differences in shadows, differences in texture between real-world images, which don't really correspond to physical 3D anchors. Luckily, and this is sort of where our big breakthrough came in, is that ARKit and AR Core and most ARKit-enabled devices also provide you localized points which say, we know that there's a point in this image which corresponds to a realistic 3D world anchor. And these sort of form clusters in both images. So what we then said was, let's look at the matches, look at where their endpoints lie in these images, pick out the matches which have the highest cluster range, and filter them down to get the best match. And these are matches that correspond to images using real 3D world anchors. So we've narrowed down from over 100 different matches, 100 different possibilities, to one really good 3D world anchor. Once we have that, we can then recombine these images and say each phone now has one really good anchor that they are reliable, is roughly equivalent in both phones. And then we can create our 3D world anchor. This anchor allows us to say each phone can now treat this point as its origin point, and every movement thereafter is relative to this point. And we can create axes in X and Y and Z. And after this, our entire setup process is complete. There's nothing else the phones need to do. They can move around as far as they want, and everything works just fine. In fact, you can then create any sort of assets you want in the real world, and they will show up relative to that 3D world anchor. So if phone number 1 creates a life-size human body, if it wants to, the other phone will see it in the exact same real-world position. And we're going to show you what this actually looks like with some real-world demos.
Great, thanks, Devesh. So we have this framework and this method of producing that anchor. What does this look like in practice? So what you see here is that step-by-step process applied to a simple image. We took a picture of a computer mouse here. And we have in that step 2 image over there, we have those AR points which are generated along with those SIFT points. Those are features of the image which we think might be common across both images. So from there, we can create those matchings, which you see with the image on the left. And then we choose those matchings using the algorithm that Devesh described with the centrality respect to those points we're confident about given to us by ARKit and AR Core. So from there, we can create an image or create an anchor as the user selects that anchor. And that's sufficient for us to be able to have an origin point in that environment. And with respect to both phones or any number of phones, place objects in the AR world. So here's a video, and we'll take a look at what this looks like in practice. Here's a simple demo. What we have here is we have views from 2 phones. Okay, this is Devesh and Ash standing over the computer, and so Ash is going to synchronize his phone now, and from there we're going to get the server is going to be sent that original image, and Devesh will synchronize his phone momentarily. And so now already you see the anchor points have come back. It's that fast, and so now Ash is going to select one of those anchor points. You see that little green circle there. And once he selects that, we have this little demo with rocket ships, but we have 2 rocket ships in the world. And what we can do now, these appear in the same location with respect to both users. And so if it appears, that rocket ship appears just to the right, sort of on the top of that computer from one perspective, and it appears in the same location from the other user's perspective. So this is a truly shared AR environment. So we can move these rockets around. For the sake of the demo, we're just moving them around. But you can imagine a game being played here. You can imagine, doing some computer-aided design with a model of some sort. And so we have a lot of flexibility here. So what does this look like in terms of our evaluation metrics? Well, we were able to get that calibration time down to 4.1 seconds by the end of our project, which is unbelievable considering the amount of time it takes to calibrate everything fully. And from there, when you move an object around, the latency is about 1/10 of a second. So it's really incredible how quickly developers are able to use everything. So finally, with regard to our evaluation metrics, I mentioned those above. And with regard to the framework,
we managed to build this in such a way that it requires 0 lines of code to execute and set up this framework, which is really incredible for a potential developer. And that's all we have. So thanks very much.
We have time for Q&A. Yeah.
Hi, yes, a couple of questions. First of all, very cool.
Thank you.
So, there's a process, I know it's a development environment, does processing happen locally on these phones, or do you have to have a connection to a cloud server? If so, is latency an issue, or, bandwidth an issue, right? Because people do this in all kinds of, Pokemon has to go out into the wilderness, right? Also, does this bolt on to an AR kit? And if so, is the API built and put in other development environments, like when Magic Leap comes out with their thing, is that going to work there?
Yeah, so 2 parts to that question. The first one, is there a server involved with that? Absolutely, Jacob can talk a little bit about the server, but we're basically sending all these points that we generate locally to the server to do some computation and sending it back. But at the end of the day, this is a developer framework. How do we make it easy for developers to use this project? And so we actually built a one-click deploy for the server, meaning that developers, when they're using our product, can just click a button, it'll spin up a server instance, give them back a link, which they can just copy, like they can just take that link, put it into their development environment, and they'll automatically have a server up and running for them. It's that simple. We wanted to make this as easy to use as possible. In terms of whether any other kit can use this, right now it's built on top of ARKit, which is Apple's device, but you can imagine a very easily, AR Core uses the same exact API as ARKit for the most part because they want developers to be able to build on both platforms. So as long as it conforms to some sort of augmented reality API, we're more or less using very basic augmented reality principles, like how far away is an object, where are the planes. It should be very pluggable.
I'm sorry, maybe you misunderstood what I asked, but the ultimate, I understand it's a development environment, but when the finished product is deployed, the person's walking
Oh,
around,
okay.
you see rocket ships, right?
Yes.
Do they need to have a good connection to the, to the web?
So yeah, so we've put a lot of optimization into this. The way we compress images is such that we don't need a lot of quality in terms of what the server sees and recognizes. So in initial calibration, that's where the highest throughput is in terms of data, right? But after that, we're sending single vectors, right? And so we're really able to minimize the amount of data that passes over the network.
Have you tested it? It's low.
Oh yeah, it's extremely fast. We've tested it over LTE. Most of our tests are over LTE. Yeah.
That's all the time we got. Thank you.
Thanks.